Learn like a pro.
Ever wonder how energy actually moves? I mean, from the light of a star millions of miles away to the sound of my voice reaching your ears, it's all built on an invisible architecture. Today, we're going to decode that blueprint. We are talking about the physics of waves.
Okay, so let's get one thing straight, right off the bat. This is the absolute golden rule. Waves move energy, not stuff. Look at this little particle here. The wave's energy comes through, gives it a little wiggle, and then moves on. But the particle itself, it ends up right back where it started. The energy is the traveler. The medium it's traveling through is just doing a little dance in place.
So, what exactly is a wave then? Well, let's put a pin in the official definition. It's really just a disturbance, a vibration, that travels. The whole point is to transfer energy without actually moving any matter. I love the analogy of a rumor spreading through a crowd. The story itself travels across the room, but each person pretty much stays put. That's a wave in a nutshell.
All right, so if the energy's moving but the stuff isn't, what does that dance actually look like? Well, it turns out there are two main choreographies, two fundamental ways this can happen. We're diving into what's called the matrix of motion, transverse versus longitudinal waves. And this visual just nails the difference, doesn't it? It really boils down to one simple question. How are the particles moving compared to the direction the wave's energy is going? In a transverse wave, the particles jiggle up and down, perpendicular to the energy's path, kind of like doing the wave at a stadium. But for longitudinal waves, the particles push back and forth, parallel to the energy's path. Think of a slinky being pushed.
So let's break it down one more time. Transverse, the particles move perpendicular, up and down, while the energy travels forward. That's light, that's ripples on water. Easy. Longitudinal, the particles oscillate parallel, back and forth in the same direction as the energy. And that right there is how sound works.
Okay, so we've got our two main types of waves down. Now it's time to get a little more technical. We're going to pull out the measuring tape and look at the actual anatomy of a wave, the key dimensions on our blueprint. Think of this graph as a snapshot, a single photo of the wave frozen in time. And what's so cool is that the shape tells you everything. See this? The amplitude? That's the maximum height from the middle. And it's not just about size, it's a direct measure of the wave's energy. Bigger amplitude, more punch. And then there's the wavelength. That's the Greek letter lambda, which is just the length of one complete pattern, from one peak to the next.
So, just to recap these key parts of the blueprint. Amplitude is all about energy. More amplitude, more energy. Simple. Wavelength is the distance for one full cycle. You can measure it from crest to crest. Speaking of which, the crest is the highest point, and the trough, well, that's the lowest point. Got it? Good. Right. So we've measured the wave's dimensions in space. But waves aren't static. They're constantly moving. They exist in time. So the next part of our blueprint is all about timing. We're switching from distance to duration, from the wave's shape to its rhythm. And when we talk about rhythm, we're really talking about two things that are just two sides of the same coin, period and frequency. The period, that's T, is just the time it takes for one complete wave to pass by. How long is the dance? The frequency, that's F, is how many waves pass by every second. How fast is the dance? And they're perfectly inverse. So if you have a really short period, meaning a super quick oscillation, you're going to have a really high frequency. It just makes sense, right?
Okay, this is a super important point, so listen up. These two graphs can look almost identical, but they are telling you completely different stories. The displacement distance graph is that snapshot in space we talked about. It gives you the wavelength. The displacement time graph is totally different. It's like a video focused on just one particle, tracking its up and down motion over time, and that's what gives you the period. One is space, one is time. Huge difference. Okay, so we have all the parts, we've got the spatial measurements, like wavelength, and we've got the time-based stuff, like frequency. Now it's time to put it all together. We're about to build the engine that powers this whole thing, the one formula that connects it all.
And here it is, the wave equation. V equals F times lambda. Speed equals frequency times wavelength. It looks so simple, right? But don't let that fool you. This little equation is the absolute heart of our blueprint. It's the master key that links a wave's rhythm with its physical size to tell us exactly how fast that energy is moving.
So, let's take this engine for a spin. Say we've got a sound wave with a frequency of 400 Hz. That's 400 wiggles a second, and a wavelength of 3/4 of a meter. We just pop those numbers into our formula. 400 times 0.75, and bam, we get a wave speed of 300 meters per second. See, the blueprint works perfectly.
So what's the point of having a blueprint if you can't use it to do something cool? Well, one of the most powerful things we can do is predict the future. Specifically, we can figure out exactly which way any particle on the wave is about to move. And for that, we have this awesome little trick called the shift method. It's super simple but incredibly effective. Here's how it works. You look at the wave right now. Then you just imagine or even sketch that same exact wave shape but shifted just a tiny bit forward in the direction it's traveling. Then you just look at a particle and see, does it need to move up or down to get to the new wave? That's it.
And here you can see it in action. The solid line is the wave now. The dotted line is the wave a split second in the future. So for particle Q to get onto the new wave, where does it have to go? Down. And particle R? It has to move up to catch its new spot. It's a dead simple visual trick that gives you the right answer every single time.
And there we have it, the complete blueprint of wave mechanics. We started with the fundamental rule, energy moves, matter doesn't. We explored the matrix of motion with our two main types, transverse and longitudinal. We measured the core anatomy, amplitude, wavelength, and period. And then we fired up the engine, V equals F lambda, the entire architecture of how energy moves, all laid out. So I'll leave you with a little puzzle to chew on, a final test of our blueprint. Let's say a wave's frequency doesn't change, it stays constant. Now, using our engine, V equals F lambda, what would have to happen to its wavelength if you wanted to double its speed? Have a think about that one.